Hello everyone, in this lecture I am going to discuss about the transmission line. This subject is related to the this topic is related to the microwave and radar engineering KEC 074, which is useful for electronics and communication engineering student of 7th sem. Now coming to the introduction part of this microwave. What is the microwaves? Microwaves are the form of electromagnetic radiation with the wavelength ranging from 1 meter to 1 millimeters, with frequencies between 300 megahertz to 300 gigahertz. 300 megahertz for 1 meter and 300 gigahertz for 1 millimeter. Microwave include the entire SHF, super high frequency band, that varies from 3 to 30 gigahertz or 10 centimeter to 1 centimeter. Frequencies in the microwave ranges are often referred by IEEE standards or IEEE designated bands LSCX, KU, or K band. So microwave in microwave is not meant to suggest a wavelength in the micrometer range, rather it indicates the microwaves are small, having shorter wavelengths compared to the radio waves used prior to microwave technology. So the microwave deals with the communication technologies in the frequency range from 300 megahertz to 300 gigahertz, and this wavelength varies from 1 meter to 1 millimeter. And microwave region in terms of frequency is from 3 gigahertz to 30 gigahertz, and millimeter wave region is from 30 gigahertz to 300 gigahertz. The wavelength can be calculated using this formula lambda is equal to c by f, that is where c is the velocity of light and it is 3 into 10 to the power 8 meter per second. So by using this formula we can calculate the wavelength of any wave. This is the frequency spectrum designation and with their wavelength and applications. So you can see here 3 to 30 kilohertz is used for is known as very low frequency and is used for navigation purpose, and 30 to 300 kilohertz is known as low frequency and is used for radio beacons and also used in navigations. 300 to 300 kilohertz is used for AM broadcast and maritime coast guard radios, and this is medium frequency. 3 to 30 megahertz is high frequency signal which is used in telephone and ship to ship broadcast and ship to aircraft communication. 30 to 300 megahertz is known as very high frequency and it is useful for broadcasting purpose, air traffic control and mobile radio services. And 300 to 3000 megahertz is known as ultra high frequency, that is UHF, and which is useful for satellite TV and radio, radar and wireless line. 3 to 30 gigahertz is known as super high frequency and used for airborne applications, and 30 to 300 gigahertz is extremely high frequency which is used for radar and security purposes. So these are the frequency ranges which are useful for various applications, and this table shows the designation with their wavelength. Now IEEE standard for microwave band designation. So previously that was known as the C band is the VHF is known as VHF, that is very high frequency, varies from 300 to 1000 megahertz, and the new designated band has been given by this IEEE. So previously it varies from very high frequency varies from 300 to 1000 megahertz. L band frequency ranges from 1 to 2 gigahertz, S band varies from 2 to 4 gigahertz, and C varies from 4 to 8. Uplink and downlink frequency, that is 4 to 6 and 6 to 8 gigahertz. X band varies from 8 to 12, that is 8 to 10 gigahertz and 10 to 12.4 gigahertz. Similarly, Ku varies from 12 to 18, K varies from 18 to 26, and Ka varies from 26 to 40 gigahertz. So these bands, if I am using any device which is useful for microwave applications, then we should know what is the frequency range and which device is useful for which frequency range, and what will be the designated band nominated by or nomination given by the IEEE. What is the advantage of this microwaves? It has wide bandwidth, high directivity, small size antenna can be used for microwaves, low power consumption and effect of fading. So wide bandwidth, the bandwidth of microwave is larger than the common low frequency radio waves. The more information can be transmitted using this microwave, so it is very good advantageous because of this point to point communication. High directivity, as wavelength decreases, directivity increases and beam width decreases. A small size antenna, as I have discussed, how will you define the size of the antenna? The antenna size can be smaller as the size of the antenna is inversely proportional to the transmitted frequency. As well as frequency increases, lambda is equal to C by F. Frequency is high, the wavelength will be low, and if the wavelength will be low, the size of the antenna will be low. So this as much higher as the frequency will be high, we have the waves of much higher frequencies. So in that case, the higher the frequency, smaller will be the size of the antenna. Low power consumption means the required power for transmitting the high frequency signal is lesser than the power required in transmission of low frequency signals. So as the microwave high frequencies, microwave have the high frequency, so this requires very less power. So effect of fading can be improved, reduced by using the high frequency signals. So it can be minimized by using the line of sight propagation techniques at the microwave frequencies. Now what are the applications? Applications of the microwave in communication, non-destructive evaluation, heating, medical sciences. So we can use this microwaves in industry, scientific, medical and domestic applications, and we can use this microwave application in our daily life, that as we are using this microwave wave in our daily lives. So in communication we can use in military or army, which is using the X or Ku band for their communication purpose, and remote sensing we are using in the radar applications, and in heating purpose we are using in our microwave oven to bake and cook the foods, and in medical sciences we are using in diagnosis of various diseases and as well as for various therapies. Some other applications of microwaves we can use in personal services like mobile data transfer, wireless LANs, Bluetooth, global navigation and positioning systems. We can also use this in infrastructure, medical science, military. So radars, microwave relay, links, satellite systems, radio astronomy and biomedical engineering. So these I have discussed about the microwave, what is the microwave, what are the frequency ranges, why they are useful in this. Now I am coming to this transmission line. So we can classify the transmission line on the basis of geometrical and electrical properties. So in geometrical properties, the multi-conductors, we can differentiate the transmission line on the basis of multi-conductor and single conductor, and on the basis of electrical we can differentiate on the basis of modes. So in transmission line we are using two type of mode, TM mode or non-TM mode. So although we are having the transverse electric, transverse magnetic field in case of transmission line, so multi-conductor transmission line includes the coaxial cable, twin lead line, parallel plates line, microstrip line, etc. And in single conductor we are using the waveguides. These waveguides are useful for various applications. Now what is the TM mode basically? So I am not interested in this geometrical, on the classification on the basis of geometrical structure or multi-conductor or single conductor. I am interested in transmission line for this electrical applications on the basis. So TM mode is a mode of propagation characterized by the electric field E and magnetic field H that are purely transverse with respect to each other and with the axis of the transmission line to the direction of propagation. Or you can say the EZ electrical component in Z direction and magnetic component, electric field component or electric component in Z direction and magnetic field component in Z direction will be 0. So a transmission line can support E mode only if there are at least two disjoint conductors in the cross section, or the medium filling the cross section is homogeneous, isotropic or lossless. So on this basis we can divide various modes. So basically there are three types of mode: TE mode, TM mode and hybrid mode. In TM mode, that is transverse electric field mode, the T waves are known as H wave or magnetic field waves, and these are characterized by the fact that they are always perpendicular to the direction of propagation. So in T wave or T mode, the electric field is purely transverse to the direction of propagation and magnetic field is not purely transverse. So magnetic field is not purely transverse, it means this is a non-zero component and electric field is a 0. Similarly in TM mode, transverse magnetic mode, this is also called as E waves, are characterized by the magnetic vector, and in this case the H field is purely transverse in the direction of propagation and the electric field is not purely transverse. So the electric component will exist, electric field component will exist and the magnetic field component will be 0. And in hybrid mode, in this case hybrid mode, T and TM modes are coupled together. So in this case neither electric or nor magnetic field will be 0. Sometimes this hybrid mode is called EH mode or HE mode. So these are the modes that are used in the transmission line. So mathematical model gives the cutoff frequencies and propagation constant for this transmission line. So we can use the various models. For low frequency, how will you decide that this is the low frequency? The length of the transmission line should be less than very less to the wavelength. And for analyzing such type of, for low frequency applications, we are using lumped element model, and for high frequency applications we are using a field model, and for medium frequency application we will use the distributed element model. But a transmission line is generally a few wavelengths long, then it is convenient to extend the lumped element model in the distributed element model. So by using this distributed model we can analyze the transmission line very well. This is the distributed model. You can see here we have assumed a series of lumped element or distributor elements where Va and I cannot vary each incremental length. So here the input is Vzt, and at a particular distance at a small increment at delta Z, I have considered that the voltage and current is Vz plus delta Zt. I have considered here that this voltage and current will depend on the length of the transmission line. So these are this is the primary constant at a small increment in the length of the transmission line. This current will be Iz plus delta Zt, and the voltage at these terminals will be Vz plus delta Zt, where R is this transmission in this transmission line, resistance and resistance, inductance, conductance and capacitance are used in per meter. So unit will be same, the quantity will be the resistance, the unit for this resistance will be ohm per meter. Similarly the conductance and the inductance can be defined, or you can consider the, so this as the primary constant of the transmission line. So here for finding this characteristic impedance and the propagation constant, we can use the KVL and KCL for an infinite line transmission, where we can get by using this KVL equation, you can get delta Vzt by delta Z is equal to minus Rzt minus L, this equation, and in the phase form, in the phasor form, you can write this Izt is equal to this. So we can write this in phasor form, dVz by dz is equal to R plus j omega L. R plus j omega L, minus sign is common, R plus j omega L Iz. Similarly, I can write here diz by dz is equal to minus g plus j omega c Vz. So by using these equations, we can find the value of propagation constant, that is gamma, and the value of z naught. So by using this equation, we can get the gamma is equal to R plus j omega L g plus j omega c, and this gamma is nothing but alpha plus j beta. This alpha is attenuation constant and beta is phase constant. Attenuation gamma is and z naught is the characteristic impedance. Z is nothing but R plus jx. So in the next lecture, I will discuss how will you find the propagation constant, how will you find the phase constant, and how and what is the effect of this, what is the effect of the length of this transmission line on the propagation constant, and what is the effect of the termination of the what is the effect of the terminated load of the transmission line on the this propagation constant and the characteristic impedance. So this is all about the basics of transmission line and applications of microwave radar engineering. Thank you.